Hello everyone, this is Sarbajit Dutta and welcome back to Educathea. So this is going to be the second portion in which we will describe black bodies quantitatively. So let's directly ask Billy to lend me the blackboard. So now we have an initial expression for E lambda. So E lambda is C by 4 into U lambda. Now we already know from our high school physics once again that C is equal to mu lambda, where C is basically the speed of light, lambda is the wavelength of light, and mu is the frequency. So what we can do is we can interchange lambda and mu and we can get an equivalent expression for E mu, which is basically C by 4 U mu. Now notice nothing will change essentially in this expression because there is no lambda or mu in this particular expression. So just the subscript will change, nothing else will change. Now my main job is to find out the expression for U mu, and if I can do that, then my job is done. So U mu is basically the monochromatic. Why monochromatic? Because we are talking about a single wavelength, a single color. Monochromatic spectral radiation density. So it's kind of the total energy divided by volume. Now let's say there are 10 waves carrying 1 joule of energy each. So the total energy is 10 joules in such a case. And if you divide that 10 joules by the total volume, then what you get is U nu. So U nu is basically the total number of waves multiplied by the average energy carried by each wave divided by volume. So U nu is basically the number of waves multiplied by average energy per wave whole divided by the volume. And we already know what volume is. Volume is basically L cube, where L is one side length of the cubic box. The number of waves will be represented by something called capital N, and the average energy will be represented by something called epsilon bar. So divided by L cube is basically U nu. Now I can write this in this particular fashion. Small n nu multiplied by epsilon bar, where small n nu is basically the number of waves per unit volume. So this is the number density. My job is now to find the number density. So in our problem we have a cubical box in this particular fashion. So yeah, this is more or less the cubical box. Notice I'm just drawing one face of this cubical box. So this is along the x-axis. Similarly, you have another face over here which I am not drawing. This is along the y-axis. And similarly, you have another face which is along the z-axis, something like this, which I am not drawing once again. So I'm just basically showing you one typical face of the cubic box. Now you see that every single wave which is generated within this box must lie within the box. So if you have a wave which is generated within this box, then it must lie within the box like this. It can also be a different kind of wave, maybe something like this, but it has to lie within the box. Now, do you recall what these kind of waves are? If you do, then I'm sure you will perfectly notice that these waves are nothing but stationary waves. Stationary waves. Stationary waves are created when you have two similar waves which are coming anti-parallel to each other, then you will get something like this, which is a stationary wave, right? So we have stationary wave formation within this box. Now my job is to find out how many stationary waves are there per unit volume, because that's what I'm calculating, right? I'm calculating the number density. So you see, for that, I might need to solve the wave equation for this, right? So we already know what the wave equation is. It's grad square phi, this is also called the Laplacian operator, is equal to 1 by c square del 2 psi divided by del t square. This is what the wave equation is. Now if you solve this in 3 dimensions, this is the 3-dimensional form, the 3D wave equation. Now if you solve this using the appropriate boundary conditions. So what are the boundary conditions? The boundary conditions are basically very simple. You see that these waves must lie within the box. So these waves will disappear at the edges of the box. So psi will be 0 at x equal to 0 and x equal to L, because this whole length is L. This is the x equal to 0 point and this is the x equal to L point. And similarly psi will be 0 at y equal to 0 and y equal to L, obviously, because same type of stationary waves will be also there along the y-axis, which I have not drawn, and psi will also be 0 at z equal to 0 and z equal to L. Now some of you might be wondering about what psi is, right? So psi is the wave function here, the wave function. What is this wave function? This wave function is any random function which has a sinusoidal variation. Just like in our water wave example in one of my last videos, we saw that pressure had a sinusoidal variation. So in such a case, my psi is pressure. In case of light, we saw that electric field had a sinusoidal variation. So in such a case, psi will be electric field, and so on and so forth. So psi is some general random parameter for which I am solving. It can be any physical quantity depending on the case. Since we are considering electromagnetic radiations here, psi would essentially be electric and magnetic fields, but for simplicity, I am just considering psi. Now if you solve this 3D wave equation by putting the boundary conditions, then what you will essentially get is psi n is equal to an cos omega n t plus bn sin omega n t multiplied by sin n1 by x by L into sin n2 by y divided by L into sin n3 by z divided by L. So this is what you will get. This is exactly the equation for a stationary wave. The relation between small n and n1, n2, n3 is something like this. N square is equal to n1 square plus n2 square plus n3 square. By the way, n1, n2 and n3 are positive integers. Positive integers. Omega n is something like this. Pi times c divided by L into root over n1 square plus n2 square plus n3 square. Now we know that omega is basically 2 pi into mu, where omega is the angular frequency and mu is the linear frequency. So mu n from this formula will be basically c divided by twice L into root over n1 square plus n2 square plus n3 square. And from this expression, n1 square plus n2 square plus n3 square is basically 2L mu divided by c whole square. Notice I've dropped the subscript mu n here. I've just written mu and not mu n. This is basically because I'm considering only one single frequency only one single color, only one single wavelength. And that's why I've dropped the index n. Now for some of you, this might be a bit overwhelming. You see, I have not solved any equation over here and I've straight away written down answers. I've done this basically because the aim of this course is to make you understand quantum mechanics. And the course is not essentially aimed at solving differential equations or aimed at explaining what waves are, essentially what stationary waves are, right? So that's why I've skipped the derivations of these solutions, but you can check it out in any standard textbook. You'll get it over there. But still, I want to give you an intuitive idea about what I have skipped in my solution. So let's consider the box once again. So this is my cubical box, right? So you see that in case of 3 dimensions, I'll write the wave equation in this particular format. A sine k vector dot r vector minus omega t plus some delta, which is the initial phase. Now you notice this k vector is basically called the wave vector, and its magnitude is 2 pi by lambda. Now this k vector has components which can be written in this particular fashion: kx I cap plus ky j cap plus kz k cap. And each of these components have magnitudes in this particular format. 2 pi by lambda x is kx, 2 pi by lambda y is ky, and 2 pi by lambda z is kz. Now let's say I have a wave which is moving like this with a wavelength lambda. I'll consider this direction as the k direction, alright? And similarly, I'll have a component of k along this axis. If this is my x-axis, then this will be kx. I'll consider this angle to be theta 1, right? And so along kx, the wavelength will be lambda x. Okay, clear? Now you notice that I've told you within this box there are stationary waves, right? So one wave will be like this, another wave will be something like this, and so on and so forth. So now let me draw these waves separately. I'll draw the red wave first. So this is what the red wave looks like, and then you have the yellow wave, right? So this is what the yellow wave looks like. Now notice that the length of this red wave is half of the wavelength, right? So this is basically lambda x by 2. Lambda x because I'm considering this wavelength along the x direction, right? So lambda x by 2 is basically the wavelength of this wave. And this lambda x by 2 wavelength is covering this entire length L. You can see over here, right? So this is L. And similarly over here, this yellow wave is one full wavelength. So lambda x, and that's equal to L. So now look that for these standing waves, I will get expressions like these. And so what I can do is I can club all these expressions into one single expression. So notice how I will write it. I will say n1 lambda x by 2 is equal to L. Notice very carefully that n1 can take only positive integral values. So n1 is 1, 2, 3 and so on. So when n1 is equal to 1, I'll have lambda x by 2 is equal to L, this one. When n1 is equal to 2, I will have lambda x equal to L, which is this one. When n1 is equal to 3, I will have 3 lambda x by 2 equal to L, which will be the next standing wave, something which will look like this, which I have not drawn. So you can see that from this single expression, I can get the pictures of the various different standing waves. Now notice from this diagram, I can write lambda x cos theta 1 is equal to lambda, right? And so cos theta 1, which I'll write over here, is basically lambda divided by lambda x. And I know what lambda x is, right? So lambda x from this expression over here is basically twice of L divided by N1. So this is what lambda x is. So N1 lambda divided by twice of L. Similarly, I will get a cos theta 2 for the y-axis. This is for the x-axis, and for the y-axis I will get a cos theta 2, which will be nothing but N2 lambda by twice of L, and for the z-axis, the z-axis, I'll get a cos theta 3, which will be nothing but N3 lambda divided by twice of L, right? Now you see that these cos theta 1, cos theta 2 and cos theta 3 are direction cosines. So cos theta 1, cos theta 2, cos theta 3 are direction cosines. And we know what the summation of the squares of direction cosines are, right? So cos square theta 1 plus cos square theta 2 plus cos square theta 3 is equal to 1. So now if you put the values of cos theta 1, cos theta 2 and cos theta 3 from these expressions, then what you will essentially obtain is the following: n1 square plus n2 square plus n3 square is equal to 2L divided by lambda whole square. Now we already know that C is equal to mu times lambda, right? So lambda is basically C divided by mu. So replace lambda by C divided by mu and you will get n1 square plus n2 square plus n3 square is equal to 2L divided by C into mu whole square. Notice that this is exactly what I had obtained over here. So this expression, equation 1, n1 square plus n2 square plus n3 square equal to 2L nu by C whole square is exactly equal to this expression, which I'll call 2. So equation 1 and equation 2 are exactly same. So I've obtained the same expression from two different methods. And this one was definitely more intuitive. Now you see that this expression is basically the equation for a sphere. X square plus y square plus z square is equal to a square. This is what a sphere looks like. If you replace x, y, z by n1, n2 and n3 and a by this 2L nu by c, then this is exactly the equation for a sphere. And since n1, n2, n3 are positive integers, they are positive integers, I've already told you. So the sphere will only lie in the first octant. So the volume of the sphere will basically be 4 pi r square dr divided by 8, where r is the radius, which is this 2L mu by c, right? Now I'll show you that there is a magical method to prove that dn will be equal to dv. This can be proved. So this is a statement that I'm making. dn will be equal to dv. What is dn? The number of waves, the differential number of waves that will be exactly equal to the differential volume. And I can show it to you. See how. Now at the very outset, let me tell you that I'm not going to solve the problem in 3 dimensions. I'm going to solve the problem in 2 dimensions, and then by using analogy, by using an analogy from 2 dimensions, I'm going to generalize it into 3 dimensions. Now why I can do this? Because there is nothing special about 3D. If something is true in 2D, or for that matter in 1D, then it is true for all dimensions. So I can easily solve my problem in 2 dimensions and then generalize it into 3 dimensions. So now I have a 2-dimensional box like this instead of a 3-dimensional box. So this is my 2D box, I'll say that this direction is my x direction and this direction is my y direction. Now you can also choose y and z or x and z, but just for my convenience I am choosing x and y. This is something that I am choosing for my convenience. Now there are standing waves which will develop within this box, right? So this is a standing wave, then this is another standing wave. Now we also know that to represent these standing waves mathematically, we can write down equations in this fashion. Something like n1 into lambda x by 2 equal to L, where the different values of n1 will give me different modes of vibrations of standing waves. So n1 equal to 1 will correspond to this mode of vibration, this standing wave. n1 equal to 2 will correspond to this mode of vibration or this standing wave. So I can also write something similar for the y direction. n2 into lambda y by 2 equal to L, and we have seen this for our three-dimensional case. So n1 and n2 gives us the various modes of vibrations. Modes of vibrations. Now since I am solving a two-dimensional problem, a stationary wave can be in a mode of vibration which will be specified by the values of n1 and n2. So if you give me the values of n1 and n2, then I can say, okay, for this value of n1 and this value of n2, this is my standing wave. So what I will do is now I'll write down all the possible combinations of n1 and n2, because all these combinations will correspond to one standing wave. So now what I will do is I'll write down all the possible combinations of n1 and n2, because for each possible combination it will represent a mode of vibration or a standing wave. So what are the various combinations of n1 and n2? You see, n1 goes from 1 to infinity in integer steps, right? So this is what n1 is, 1, 2, 3 dot dot dot. Similarly, n2 is also like this, 1, 2, 3 dot dot dot. They are positive natural numbers. So all the possible combinations will be something like this, 1 comma 1, then you will have 1 comma 2, then you will have 1 comma 3 and so on. You'll also have 2 comma 1, 2 comma 2 and so on and so forth, right? Where the first value indicates n1 and the second value indicates n2. Now instead of writing this in this particular fashion, I can also plot these points in a graph so that I can visualize my problem, which will help me in understanding this problem better. So now I have plotted the various combinations of n1 and n2 in a graph. So this direction represents my n1 values and this direction represents my n2 values, where each of these points, each of these lattice points represents a particular combination of n1 and n2. Like this point corresponds to the 1 comma 1 point, this point corresponds to the 1 comma 2 point and so on. So now the question that I'm asking is, what number of points, because the number of points are basically the number of standing waves, because each point or each combination of n1 and n2 corresponds to a particular standing waves. So the number of standing waves is the number of points. So what number of points lie between nu to nu plus d nu frequency range? Because remember, that's what our ultimate aim is. We want the energy distribution between nu to nu plus d nu. Now the thing is, frequency nu is related to radius r. We had seen for our 3D case that r is equal to 2L nu by c, right? So nu and r are related. So the question now becomes, what number of points lie between circles of radius r and radius r plus dr. So the question transforms into a new question. So what I will do is, I'll draw a circle of radius r. So this is my circle of radius r. this is r, and then I will draw a circle of radius r plus dr, which is this one. This radius is r plus dr. Now the hatched area, which is this hatched area is basically the segment between the two circles, between radius r and radius r plus dr. So this is my dr. So now the question that I'm asking is, what are the points which lie between this area segment, between this hatched area? So let's try to count. This is point number 1, this is point number 2, this is point number 3, point number 4, this is point number 5, this is point number 6, this is point number 7, this is point number 8, this is point number 9, this is point number 10, this is point number 11, this is point number 12 here, and I've missed a point here, this is point number 13. So there are total 13 points which lie inside the hatched area, Now I'll do something, I'll calculate the area of this segment. So now I'm calculating the area of this segment. So area of this segment is nothing but 2 pi r dr divided by 4, right? Because 2 pi r dr is the area segment for one entire circle. This is 1/4 of a circle, so 2 pi r dr by 4. Now you see that dr is basically 1. The distance between two circles I have taken as unity, okay? The diagram has been drawn in this particular fashion. You might not be able to see it just from your computer screen, but if you take scales and measure this distance, then dr will be 1. So trust me, dr is 1. And similarly, if you measure the radius r, then you will get 8 units. So dr is 1 units and r is 8 units. The job is simple, just take a proper scale, plot this and measure what r is and what dr is. If you do it, you will get dr equal to 1 and r equal to 8. So I am putting the values here. So 2 pi into 8 into 1 divided by 4. If you carry out this calculation, you will get something like 12.6. Can you see the uncanny resemblance between 13 and 12.6? 12.6 is almost equal to 13. Now wait a second. So the area of the segment is numerically equal to the number of points in the hatched area? Is it true? Well, it turns out that it is actually true, and this approximation becomes even better if you take a larger dr. If you take dr to be quite large so that many points are actually included between the area segment, then you can say that the area segment is actually a continuous one filled with points. So these points which I have drawn with black, these are discrete points, right? But if there are many points like these, then it will make a continuous space, it will make a continuous area strip, and so the number of points in that case will be exactly equal to the area. So for larger dr, area of the segment is exactly equal to the number of points in that segment. So if I generalize it to 3 dimensions, then I can say that dn, that is the number of points within the differential volume, will be equal to dv, that is the differential volume itself. This is a wonderful and magical approximation that we can see, and I hope you have understood this. So now that we have proved that dn equal to dv, what I want to do is I want to put down the value of r over here, and I want to give you an elaborated expression. So 4 pi 2L nu by c whole square, if r is this, then dr will be nothing but 2L by c into d nu. So this is what dr is, 2L by c into d nu divided by 8, which will give you 4 pi mu square d nu divided by 8 into c by 2L whole cube. This is what you will get. Now, the number of modes of stationary waves per unit volume, which I'll write as n nu d nu. N nu, because for a fixed frequency, is basically dn, the total number of waves, divided by L cube, the volume, the number density. This was the definition of number density, and that will be nothing but 4 pi mu square d nu by 8 into c cube into 8 L cube divided by L cube. So L cube and L cube will get cancelled out, 8 and 8 will get cancelled out. So you will have 4 pi mu square by c cube into d nu. But hold on, this is not the answer. In case of waves, we have two states of polarization, E parallel and E perpendicular. So I have to multiply this expression by a factor of 2. This is what I have to do. So my final expression for n nu d nu will be basically 8 pi nu square divided by c cube into d nu. I've multiplied this 2 because there are two states of polarization, E parallel and E perpendicular are two states of polarization. So from this expression we can get n nu is equal to 8 pi mu square by c cube. Now we already had E nu, which was c by 4 into u nu, and u nu was n nu into epsilon bar, and n nu is this. So this will be c by 4 into 8 pi mu square by c cube into epsilon bar. If you multiply a d nu to both sides, then you will get the distribution of this particular format. Now our job is to find out what epsilon bar is. Now trust me, this is the most difficult job to do, and there were many scientists who actually tried to derive the expression for epsilon bar and they failed. So in our upcoming lecture we will show you how one can calculate the value of this epsilon bar and exactly get the shape of the curve that we had drawn for blackbody radiations.
Thank you so much for watching this video. Do not forget to like, comment and share this video with your friends as much as possible. And also don't forget to subscribe to the channel, because that would serve as a motivation for me to come up with more such beautiful videos. Also kindly press the bell icon over there so that you get a notification each time I upload a new video. Don't forget to check the description box down there for more updates, and have fun and enjoy science.